Hello everyone, welcome to this presentation on sediment transport in the Torata River located in the Moquegua region. Career Professional School of Civil Engineering, course Hydrology, teacher MSc Cuentas Sólidos Mar, team number 12, Clavite Apacho, Yulisa Ida and Waman Arana Davis. Introduction. Sediment transport is a fundamental process in river dynamics which has significant implications for water resource management and civil infrastructure. In the Moquegua region of Peru, the Torata River plays a crucial role in both water supply and landscape configuration. Understanding sediment transport processing in this river is essential for the design and maintenance of infrastructure such as bridges and canals, and for the management of which relates to erosion and sedimentation. This article focuses on the study of sediment transport in the Torata Bight area. Maintaining several calculation and analysis methods, in particular the application of the Meyer-Peter and Meyer method implemented in Python is explored to calculate bed sediment transport. This method, wide uses in river engineering, allows to accurate estimate the amount of sediment transported by the water flow providence, valuable data for infrastructure planning and management. Objectives number 1. Evaluative calculation methods compare different approaches to calculate sediment transport in the Torata River. Number 2. Implement a method in Python. Develop a model in Python based on the Meyer-Peter and Meyer method to calculate bed sediment transport. Number 3. Calculate sediment transport rate. Determine the amount of sediment transported in the Torata Bight area. And number 4, analysis results. Evaluate the relevance of the result for infrastructure and water resource management. Basic concepts. What is a sediment? In river hydraulics, sediment is any granular material, heavy that water that is transported at some point by the current and the deposit. It is made up of non-cohesive materials that can be silt, sand, gravel, and sometimes stones. Sediments originated from the erosion of a basin. Basin erosion is natural process that is due to the action of external agents such as water, wind, and frost. And since rivers are the drainage elements of the basin, the water they carry drains the sediments from the erosion of the basin. Sediment properties. We have the size where the particle classification is according to the American Geophysical Union. Then the nominal diameter, which is the diameter of a spray but whose volume is equal to that of the particle. Screening diameter is the width of the opening of the mesh door which the particle is passed with considering actual shape or density. Sedimentation diameter. It is the space of each terminal of the spread that has the same diameter and specific width as the particle falling in distilled water at 24 degrees centigrade temperature with relative density 2.65. Shape. In river beds particles, the shape factor is approximately 0.7. It is determined by the following equation. Density. Particle density del whose the amount of organic matter and minerals in a sample. Relative density. It is the relationship between the density of the solid with respect to water. For quartz particles, the relative density 2.65. Specific weight. It is the specific weight of the particle per unit volume. It is also the product of density by gravity. Relative specific weight. It is the relationship between the specific weights and the specific weight of water. Specific weights submerged. It is the difference between the specific weight of the solids and the specific weight of the water. Par rate. It is the speed with which a solid arrives in a unlimited flows mass and a reset. Transport of solids at the bottom. The drag material is made up of the largest particles which are permeable in contact with the river bottom and which roll or sails. The speed of a solid particle transported as its material is generally lower than that the corresponding speed of the current. It is generally associated with the noise of the current. To calculate the transport of solids with material, the nature of the following function must be found. Du Bois formula, where we have bit solid transport, a transport parameter that depends on the particle diameter, traction force and traction force. Mayer, Peter and Mayer formula have under water and have out of water. Where we have solid transport and solid transport. And Einstein-Brown formula. It raises the relationship between the parameters transport intensity and flow intensity. Where is the Shell's parameter? Where transport of heavy bed sediments out of water, kinematic viscosity, specific weight of solid materials, specific weight of water, acting shear stress, and a relative specific weight.
Result: transportation in the bottom and suspension on the Torata bridge with Python. Before calculating the sediment transport at the bottom, it's necessary to collect the necessary data to apply the corresponding formulas. Below you can see the properties of the water and the sediments, as well as their granulometric characteristics. Cinematic viscosity of water at 10 centigrade is 1.31 multiplied by 10 to the power of 6. A specific weight of water is 1000. A specific weight of the sediment is 2468. The gravity is 9.81. The specific gravity is 2.468. Charge is diameter. D50 is 3.149 and the diameter of 90 is 18 11.263. The results of the hydraulic simulation with head RAS showed for a maximum daily average flow of 11.28 cubic meters per second is the water surface is 9.1 meters in the control section ID 300. From the graph, a depth of 0.8 meters is observed. The slope deflation is 3.93%. The material involved about roughness coefficient of the Torata River section is 0.024 degree of irregularity is 0.006. The cross-section variation is 0.005. The relative effect of obstruction is 0.01. The vegetation is 0.005. Degree of Mender effects is 1. Then the roughness coefficient of the Torata River section is 0.05. So, with about that, the bottom sediment transport can be calculated with the help of Python. First, we insert the values of flow depth in meters, the channel width in meters, median diameter, d50 in meters, diameter d19 in meters, bed slope, sediment density, specific weight of water, and manning roughness. Second, insert the sediment forms to calculate the bottom sediment transportation. To do this, you must first calculate hydraulic radius, shear stress at the bed, and the critical shear stress. Finally, calculate the solid transport with water and solid transport with hot water. Then solve the forms and present the results with prime. This is the result. The shear stress of the bed is 26.74. The roughness coefficient is 20. Manning roughness is 0.05. Roughness coefficient is 50.65. And coefficient and R is 0.02. Roughness coefficient is 0.25. Critical shear stress is 0.22. The solid transport with water is 12.8338. The solid transport with hot water is 21.5761. And the total transport is 196.343. Discussion. According to Ramirez R. 2021, the development of engineering in the 21st century brought with it the emergence of new information technologies with present new challenges in their use and practical application. The need has been created for more versatile programming language with similar or greater capacity than the classic Fortran 77, which has led to the development of languages such as the R language and Python. Therefore, through the present studied application of the Python programming language in the calculation of sediment transport is demonstrated, being more practical and faster than the manual method, in addition to providing the opportunity to automate the calculation and increase the complexity of the same. Conclusion. In conclusion, the objective of calculating the bottom sediment transport in the Torata Bridge area was successfully achieved through detailed analysis and precise measurements. We determined that sediment transport rate is 196.343. This information is crucial for informed decision making regarding maintenance and structural improvements, ensuring the bridge safety and functionality for the foreseeable future. The thorough investigation has provided valuable insights, confirming the successful fulfillment of our objective. That's all. Thanks.